Okay, with photoelectron spectroscopy, or PES, it's actually a way that scientists have used to determine ionization energies, trends as far as electron affinities, um, bonding patterns, etc. And the actual science behind it, we'll talk about it in class. But the results of PES is this. Now, first of all, before we look into all these arrows, let's take a look at this chart here. You notice the X and Y axis, okay? The y-axis actually is not labeled, but this is relative number of electrons. Okay, relative number of electrons. The x-axis is ionization energy. In other words, the energy added to strip away electrons, to remove electrons. Notice 0 is over here, and it increases to the left. Okay, so just be careful with that you interpret this correctly. So the way we're going to see this, hold on, let me get rid of all this stuff here that I just drew. The way we're going to look at this is like this, okay? If you take a look at this electron configuration, okay, this is what, for potassium, okay? There's potassium. And you'll notice that right here, this outer electron is represented by a small little hump there, a small little curve, and it's the easiest. It requires almost no energy to remove away that single electron, that one electron, okay? So there's the one electron there, okay? Now, to remove the next ones, you should have one that's 6 times higher than this hump here. So we have a hump that's 6 times higher. So that's 3p6. This hump should be twice as high as this one, and it is. That's S2, P6, and so on, okay? All the way down to these. Now, why does it take so much energy to remove these? Because they are the most closely held electrons. Okay, so it takes the most energy to remove the inner or core electrons. It takes the least amount of energy to remove the outer ones because there's more shielding effect. Okay, let's look at more drawings. This is the valence this is the ionization energy for, it asks for which spectrum, okay? For which spectrum is this? So this looks like it's a third, so this looks like it's 2 electrons here. This looks like it's 6 electrons. This is 2 electrons, so, all right, and so on. And this is the other one here. This is another 2 electrons. So what ends in 1s2, 2s2, so that's 1s2 right there. There's 2s2 right here. Here's 2p6 right there, and here's 3s2. It looks like it's magnesium. Okay? Excuse me. Okay, so that ends in 3s2. That's magnesium. So 2 plus 2 plus 6 plus 2 is 12 electrons. And that's the same as magnesium. Okay? Now check out this one. A little bit different here. So this is scandium. And scandium is element number 21. Okay? Element number 21. So we have some questions here. The 1s peak occurs at the 400, so 1s is all the way down here. It's not shown, okay? That's what it says up here. So it says, which subshell is represented by the 0.77 peak? Well, there's that guy right there, the 0.77 peak. Now, this one's a little bit of a strange question. So if we do scandium, do the electron configuration, it's 1s2, 2s2p6, 3s2p6, 4s2, 3d1. Okay, we know the 3d1 is going to be lost first. The 4s2 is going to be lost first. I just screwed that up. It's the highest occupied energy level. So this is the 4s2. Remember, the electrons from the highest occupied energy level are lost first. This is the 3d1 right here. The 0.77 is the 3d1. Okay, that's the next electron lost. Notice it's very close to the 4s2, but not quite the same. Okay, it takes a little bit more energy. Okay, now the reason for this energy difference, slight as it is that we've already lost electrons and now there's more protons in the middle. In other words, Zeph has increased. The effective nuclear charge has increased the more you lose electrons. So which subshell is represented by the 0.63 peak? I think we already answered that question. How sure are your answers to A and B? Write down the electron configurations. We're pretty darn sure, so let's move on. How can this graph be used for proof that the 4s subshell fills before the 3d subshell? And again, it just says that there's less energy to fill that 4s. Okay, less energy to fill the 4s than there is 3D. Okay? I think that's all I have. Oh, one more. Okay, why are the fluorine peaks to the left of the boron peaks? Okay, so here's fluorine is in pink and boron's in purple. So if we take a look at fluorine versus boron, let's take a look at boron and fluorine. So this is 1s2, 2s2p5, and boron is 1s2, 2s2p1. Okay, now, so why would all the peaks of fluorine be to the left? So notice we have our fluorine here, fluorine, fluorine, boron, boron, boron. Okay? And this has to do with effective nuclear charge. Okay, fluorine has more protons in it than boron does, so it's going to hold the electrons closer to it. We know that fluorine is also a smaller atom than boron, according to our periodic trends. Why is that? Because Zeph. It has a greater effective nuclear charge, and they're on the same period, so fluorine will be smaller than boron. Therefore, fluorine is harder to remove electrons than boron is because they're held tighter to the atom. Why? Because there's more protons in the nucleus. Okay? Why is there one peak in fluorine that is so much taller than the others? This ends in S2P5. This one's S2P5, which is this one right here. Okay? I'm sorry, I said S2P5. Excuse me, it's 2P5. Let me clarify, it's 2P5. That's the 2P5 peak. Okay? And that's all I got. I don't think I should have had that there, so I'm going to ignore that. And that's it for PES. So if we'll talk about this more in class. I have a handout that's going to come out too. So if you have any questions, go ahead and email.